This is section 8.3. We're going to be talking about simplifying radical expressions. Like fractions, radicals have a simplified form, and we are always supposed to write our answers in that form. Mainly, we have been dealing with roots that were exact. These are not going to be roots that are exact. We're going to be talking about how to put them in the correct form. We have some new properties. I've referenced a couple of them already. Notice right here that if we have the same index and we're multiplying radicals, as long as they have the same index, we are allowed to multiply underneath. This also works backwards. If I have things multiplied underneath a radical, I'm allowed to split them up. Similar here, if we're dividing two things with the same index, we are allowed to put them as a single fraction under that same index. And we are also allowed to take a fraction under a radical and split it into two. We've been using this one. Now this is a different one. Okay, this is really exactly based on reducing fractions. If I have a radical with an index and this has a power that are both divisible by the same thing. So say these are both divisible by 2. This says I'm allowed to do that. Now, why is this true? Think about taking this and rewriting it as a fractional exponent. Remember, what is inside is the numerator, what is outside is the denominator. So if I just take this and I rewrite it as a to the k over m over k over n, you would reduce this fraction to get a to the m over n. This is your index, this is your exponent. This comes directly from reducing the fractional exponent. Okay, so let's talk about what we mean by being a simplified radical. We're going to be coming back to a lot of this. The radicand, which is the part under the radical, has no factor raised to a power greater than or equal to the index. An example of something that would not be simplified based on this rule would be the cube root of x to the 8th. And that's because the 8 is larger than 3. We haven't talked about how to fix this yet, but that's something that would need to be fixed. The radicand has no fractions. We're not allowed to leave a fraction under a radical, so we're going to have to split it up. Not a difficult step. No denominator has a radical. We will cover this mainly in section 8.6, which when I was teaching with a different book, it was section 19.5. You don't have to worry about that. So we talk about this a little bit, but we really learn how to take care of this in a later section. Exponents in the radicand and the index of the radical have no common factor except for 1. This is what I was talking about right here. If you look at this, the inside exponent is smaller than the radical, so the index. So this is okay by this first rule, but it is not okay because both of these are divisible by 6. Okay? So in order to get this simplified, we would need to use this last property here. Okay. Now there is a warning here. You want to be careful that you don't let the index or the exponent drift. For example, if you aren't careful, x cubed times the square root of x can easily become x times the cube root of x. You may want to exaggerate the space between your variable if it has an exponent and the radical, or similarly here, if you have an index other than 2, and you have a variable in front. You may want to exaggerate that. Also, when you're entering your answers into My Math Lab, you need to be really careful that those things are separate or the program will count your answers wrong. Okay, so we're going to start using some of these properties and just see where we end up. Okay, so I have my properties written on an index card, so it's easy to reference. I have the square root of 10 times the square root of 3. These both have the same index of an understood 2. So we are allowed to multiply underneath. This is the same thing as the square root of 10 times 3, which is the square root of 30. Now I mentioned early on, I think section 8.1, that these smaller calculators have some great features in them. And one of them is that they do simplify smaller square roots. They will not do this for cube roots or any other index. And they won't necessarily do this for large numbers. So we have to know how to do all of this by hand. Everything we're talking about here in this section, we have to know how to do by hand. But our calculators can check us on some of these. If I do the square root of 10, make sure you get outside of that radical sign, times the square root of 3, it tells me it's the square root of 30, which is very useful. In section 8.1, we were interested in getting decimal approximations, and we had to use this button here. When we're talking about simplifying radicals, we generally do not want an approximation. You will not give a decimal approximation unless you are specifically asked for one. Okay, so let's try this property with the square root of 7 times the square root of 5xt. We are allowed, since both of these are square roots, we are allowed to multiply underneath the radical. This is 5 times x times t, but we are allowed to multiply the 7 and the 5, so this is equivalent to the square root of 35xt. Like I said, your calculators can help you a lot, but they also can't deal with variables. So we really do have to be smarter than our calculators. They're going to be a tool for us, not the way to find the answer. Okay. So let's simplify the square root of 16 over 49. We've talked about this already, but we're really using this property that says if we have a fraction under a radical, we can split it up into the root of the top over the root of the bottom. So this is the same thing as the square root of 16 over the square root of 49, which is 4 over 7. Sorry, brain left me for a second. Okay, now the cube root of 216 over the cube root of 125. This is the cube root of a fraction, so we use the same property we did above. Okay, and these may not be roots that you remember very well, so let's do the cube root of 216, and that is 6. And you probably recognize the cube root of 125 because we dealt with it a lot when we were doing sum of cubes and difference of cubes. It is a 5. So this answer is 6/5. Okay. So let's do negative on the outside, 4th root of 625 over y to the 4th. Dealing with variables inside radicals is actually easier than dealing with numbers, okay? First of all, there's a negative on the outside. That means my answer is negative, okay? Now this is the 4th root of 625 over the 4th root of y to the 4th. Now we were told early on that if you had an even index, then we had to worry about absolute values. We do not have to worry about that anymore because we are told in all of these problems that our variables are positive numbers. So we don't have to worry about absolute values, where the absolute value would be redundant. Okay, so my answer is negative. I need to find the 4th root of 625, and that's 5. So negative 5 over, these indices are the same, so we have just y. Another way of thinking about this, and we'll be using this a lot more as we go on, is really you ask yourself, how many times does this divide into this? It goes in 1 time, so your exponent here is a 1. But normally, of course, we don't write the first power. So your answer would be negative 5 over y. Okay. We're going to be using prime factorizations to simplify other types of radicals. The smaller, like I said, the smaller scientific calculators, like here, we'll do some of these. But we're going to calculate some prime factorizations, and I'm going to do them neatly on a separate sheet of paper because these are often reusable. There's no reason to keep doing work over and over again if we have it already. And definition of prime numbers, these are things that are divisible by them only by themselves and by 1. The smallest prime numbers are 2, it's the only even prime number, 3, 5, 7, not 9 because 9 is divisible by 3, 11, 13, not 15, because 15 is divisible by 3 and 5, 17, 19, 23, and so on. There are an infinite number of prime numbers. In general, though, they're going to give us things that have small primes in them so that they're easy to get the prime factorizations. We will talk more about this in the next video.